In this example, a 5 kilogram body is dropped from a great height. Given a gravitational constant of g meters per second squared and air resistance proportional to the speed v meters per second, given the constant of proportionality is 1/8, find the velocity at time t. So this question, we do now have air resistance coming into it, which is proportional to the speed. Now, the speed there is important because the air resistance is always going to go opposite the direction of the motion. So if the body is going up, air resistance would go down, and if the body is going down, as in this example, then the air resistance will go up. So the direction will depend on the direction that the body is moving in. So the first thing I'm going to do here is draw a bit of a diagram, and I'm going to make the origin the point at which I've dropped the body from. So it's going down, and we know that at any point in its motion there is a downwards force of its mass times the gravity. And we also know that there's an upwards force of the air resistance. Now, it told us that the air resistance was proportional to the velocity, to the speed, with a constant of proportionality of 1/8. So normally I'd write kV there. Now, we can choose really here if we want to have our direction, what our frame of reference is in terms of negatives and positives. I'm actually going to make downwards the positive. So there's positive and there's negative in that direction. So this mass times gravity is going in a positive direction, and the kV is going in a negative direction because it's going back up. Now, we know that it is dropped, so when time is equal to 0, velocity will equal 0, and we'll also call that the point where x equals 0. So I'm just going to write here that this is 1/8v. So the resultant force, or the net force on this motion, our force, it's got that mg going in the positive direction, and it's got 1/8v going in the negative direction. And we know that our force is equal to our mass times acceleration. So our mass in this case is 5. So 5 times acceleration is equal to the mass times the gravity. So 5 times the gravity minus 1/8v. So the first thing I'd like to do is just actually divide everything by 5, because I need an equation for my acceleration. So that's going to become v on 40. Now, because this equation is in terms of v, I'm going to change my acceleration into dv dt. So because we know that that's what it is. Now, just out of interest too, it would be equivalent to write this equation as, instead of v, we could go x with 1 dot over 40. And there is an example in your textbook where it works like that. And so this line would be dx dot dt equals g minus x dot on 40. There's actually also an example where it's with respect to x down here. So you've got dx dot on dx. So it can get a little bit confusing. You've got to be a little bit careful with which variable is which. Now, I'm going to use separation of variables for that. So I'm actually going to change dv dt into 40g on 40. So 40g minus v on 40. I could flip each side. I've got a preference of separating. So I'm going to make that dv over 40g minus v, so that's all the v's over there. I could move the 40 too if I want to, but I might just leave it where it is. So equals dt on 40, and integrate each side. Now let's put some endpoints on that integration. So we know that our v was initially 0 at time 0, this is our t, and we want to know what our v is going to be at time t. So the v and the t there we don't know at this point. Now we've got a minus v here, so let's turn it into a log, so we need a minus at the top, so a minus out the front. So now the top is the derivative of the bottom, so that would be negative log 40g minus v. Just notice here too, v couldn't be equal to 40g in this equation. That would be a problem there. So v can't be equal to 40g there. On this side, I've got t on 40. Let's put our endpoints onto each side of that. So 0v. So plugging that in now, we have negative log of 40g minus v, plugging in v to v, minusing, so it's going to become plus because of that negative, log plugging in 0, so log of 40g. Now g is positive, I don't need those absolute values, but that's fine. Plugging in t to this, I get t on 40 minus plug in 0, 0. The question asked for it to be an equation for velocity, so we do need to rearrange this and make it v equal to. So first of all, I'm going to collect up these using my log laws. So I'll put the positive one on top and the negative one on the bottom. That's just now t on 40. Let's take e of each side, so 40g over 40g minus v is equal to e to the t on 40. Let's flip it to get the v in the numerator, so 40g minus v over 40g, this is 1 over, so that's going to be e to the negative t on 40 times by the 40g, so 40g minus v equals 40g e to the negative t on 40. Okay, I might take the negative of each side, so negative v is going to be v minus 40g equals negative 40g e to the negative t on 40 plus the 40g, so v equals 40g minus 40g e to the negative t on 40. I might just factorize that as well. So 40g 1 minus e to the negative t on 40 is my solution. In part B, we're asked to actually sketch the curve of the velocity against time. So I'm just going to, we know it's like an exponential shaped curve, so we've got a general idea of the shape of the curve, but there are some transformations applied here. I'm just going to plug in a few values. So if t is equal to 0, this becomes 1. Anything to the power of 0 is 1, 1 minus 1 is 0, velocity would be 0. So there is the point there, t0, v0. Now, the next thing I'm going to do is I'm actually going to say what happens as t goes to infinity. Where does this graph go? Because I know an exponential function often will go like that. With transformations, it might actually look like that. There's all sorts of things that it could potentially look like. Now, let's have a look. So if this is infinity, then I've got negative something enormous. And e to the negative something enormous is 0. We know that that typical exponential curve, I'm looking way down here, and that's pretty close to 0. So 1 minus 0 is 1, so 40g times 1. So in that case, it would just be 40g. So as we go to infinity, as time goes to infinity, our velocity tends towards 40g. So we've actually got an asymptote up here at 40g. And our curve looks like this. Obviously it never touches the asymptote. If you wanted to, you could plug in a few more values to see that shape. Part C asks us to find the terminal velocity of the body. Now we've actually already done that. So what you can imagine is this thing is falling and it's getting faster and it's getting faster and it's getting faster. because of gravity, but at the same time, the air resistance is slowing it down. And there's actually a limit to how fast it can get. So what we're saying is, what is the maximum this can actually be? And we just saw that the limit as t goes to infinity of the velocity is equal to 40g. So you're just saying what happens as time goes on to that velocity. So the terminal velocity is 40g. Another way of finding that would just be by maximizing our function. And so the maximum point happens when the acceleration is equal to 0. Now, we know the acceleration equation from before. We know that acceleration is equal to g minus 40 on v. And let's see, when does that equal 0? Let's add the v on 40 to each side. Just turn it around. So v equals 40g. We got the same answer. In part D, we're asked to find the distance travelled at time t. So basically just an equation for its displacement, or in this case it's distance and displacement, really the same thing because it just keeps falling. So here's our velocity curve. Now remember, velocity is equal to the derivative of displacement over time. So that equals 1 minus e to the negative t on 40. Now this is fairly straightforward because bringing the dt up, I've got the integral of dx equals the integral of 40g 1 minus e to the negative t on 40 with respect to time. Let's put our endpoints on. So time goes from 0 to t. Now our dx starts at 0. Remember, positive was going down, so we're going down, 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 down as far as x. So let's integrate that. That just becomes x from 0 to x. The 40g is just a constant. I could just leave that out the front. The integral of this part with respect to t1 becomes t. I'm going to be dividing by the derivative of the inside. So I'm going to be dividing by negative 1 on 40. So that's going to be plus 40 over 1. Dividing by negative 1 on 40 is the same as multiplying by negative 40. E to the negative t on 40, and that's from 0 to t. So let's plug in those endpoints. This is just x minus 0. 40g can just stay right up the front. So let's plug in t first. So t plus 40e to the negative t on 40 minus, plug in 0. So we've got 0 plus 40e to the 0, which obviously is just 1. So x is equal to 40g. We've got a t there. Now that's just a minus 40, so plus 40e to the negative t on 40 minus 40. There's our equation. Okay, in example 5, a 1,500 gram particle is projected vertically upwards with initial velocity capital V, gravity, and an air resistance of 0.03 v squared. Both act on the particle. Find the maximum height reached by the particle and the time taken to get there. So this is actually a pretty big question. There's a lot of detail there, and it's not scaffolded in any way. So the first thing we want to do is draw a force diagram. So let's make the ground 0. So at t equals 0, our x is equal to 0, and our velocity is equal to capital V meters per second. The particle is fired directly upwards. Let's make this positive and this negative, so it's going up. Now the force is acting on the particle. We know that there's a force going down. There's gravity acting on the particle, so the downwards force, of course, is the mass times the gravity. And there's also air resistance. Now, air resistance always goes in the direction opposite the motion. So because it's going up, our air resistance will go down, and that's equal to 0.03 v squared. So our equation for the forces acting on the particle are the mass times the gravity going down, and also the 0.03 v squared, which is also going down. So those things are both negative. And of course, our force is our mass times our acceleration. Now, I'm still in terms of m here. I'm going to divide through by m. So my acceleration is equal to negative g minus 0.03 v squared over m. Now, we were told it's 1,500 grams, but I'm not putting a 1,500 in here because this needs to be in kilograms. So that's going to be a 1.5. Now, I'm going to put that 1.5 in my calculator to see what that equals. So that equals 0.02, which is 1 on 50. So this thing here is 1 on 50, so v squared on 50. There's my equation for the acceleration of the particle. But we're asked to find the maximum height, so we need to keep going here. We need an equation that has x equals. Now we've got v and we've got, that's dv dt, but dt is not very helpful. What if we use our v dv dx? It's got v, which we need, and it's got dx, which is what we're looking for, so that could be really helpful. Let's just add these fractions. So this is going to be 50 on 50. So negative, I might bracket, 50g minus v squared all over 50. Okay, let's separate our variables. So let's put the v's on the left. So v dv over 50g minus, that should be plus v squared. I might just leave that negative over this side, so negative dx on 50. Let's integrate each side of that. Now our x, we started at 0 and we're going to go up until it's at a height of x. Our velocity started at capital V and it's going to go up to whatever little v it is at the time. Now we've got a v squared here and a v here, so we're looking at a log. So let's just double that, which means we need to halve that. So we've got half the log of 50g plus v squared, and that goes from capital V up to little v. It's going up, the forces are pushing down, it's actually slowing down. I've got that last bracket. The integral here is negative x on 50 from 0 to little x. Let's plug in those endpoints. Now I'm going to do a little bit of a shortcut here. Because I've got a log minus another log, it's the same as the log of a fraction. So if I plug in little v, I'm getting 50g plus little v squared. When I put in capital V, I'm minusing it. They've both got the half in front. That's a capital V there. Just be really careful with that. Put in x, I've got negative x on 50 plus 0 because I'm minusing a negative. So one thing I was just thinking is I could have done this until v equals 0 because it's going to reach its maximum height when little v is 0. I might just leave it for now. We'll get this equation for displacement out and then we'll plug in the 0 afterwards. So I'm going to multiply each side by negative 50 and turn it around. So x is equal to negative 50 on 2, so let's go 25 log 50g plus v squared over 50g plus capital V squared. And we want the maximum height, and the maximum height of course happens when v equals 0. So max height when v is equal to 0. So x equals negative 25 log, so the top will just be 50g over 50g plus capital V squared. That is the maximum height reached. One thing that's interesting there is to think about, is that a positive or a negative number? I mean, it looks like a negative, but if you look at this denominator is always going to be bigger than that numerator. So this is less than 1. And the log of something less than 1 is also a negative. So this is definitely a positive value. Now we were also asked the time taken to reach that maximum height. And for that, I'm actually going to go right back to this first line, and instead of using v dv dx, I'm just going to use dv dt, because I want time, not displacement. So instead of this line, I'm going to write dv dt is equal to this same thing, so negative 50g plus v squared over 50. Let's just put some brackets around that so we know that negative is definitely right on the outside. Okay, let's separate our variables. So we've got dv on this side, 50g plus v squared. So we're seeing this time that's not a log, equals negative dt over 50. Let's integrate each side. Of course, I could have put that integral after that negative if I wanted to. So let's think about our endpoints. So with velocity, we started with capital V. And again, I might actually use the 0 this time because we are going up to when velocity is equal to 0. And for our time, we started at 0 and we're trying to find the time, so that's still an unknown, so we're just setting that as a t. Okay, let's integrate that. Now look at this, that's a tan inverse, isn't it? So that's going to equal 1 over the square root of 50g tan inverse v over the square root of 50g, and that's from capital V to 0. And that's going to be, this side is just t, or negative t on 50, so negative t on 50 from 0 to t. Okay, I've a bit squished for room here. Let's plug in a few endpoints there. So we've got 1 on the square root of 50g. I'm plugging 0 in first. That's just 0. Tan inverse of 0 is 0. So actually let's write it. So 0 minus, I've left that right out the front, tan inverse of capital V on the square root of 50g. Close up some brackets. And that equals negative t on 50 minus negative 0. Now we were asked to find the time taken, so I'm going to leave that as t equals. So I just need to multiply each side by negative 50. Now this is actually a negative because 0 minus, so the negatives are going to cancel out. So I'm going to end up with t equals just positive t here because it times by negative 50. 50 over root 50g tan inverse capital V over the square root, just be careful with that square root there, 50g. Actually, if I wanted to, I could look at these square roots of 50 and simplify that a little bit. Let's just make that the square root of 50 on g, tan inverse, capital V on the square root of 50g. That is the time taken to reach the maximum height. In part B, we're asked to find the equation for the height of the particle on its return journey. And it's kind of like we need to start all over again. So our force diagram this time, we're starting right up here. Now we've got a choice here in whether we set this equal to 0 or whether we set it equal to the maximum height that we found in our previous example. Let's think about that for a minute. So it's going down. And again, our frame of reference, whether it's positive or negative. But we are starting again. So this is now our t equals 0. And at this point, its velocity would be equal to 0 because it's a stationary point. Let's just think a little bit more about our x for a moment. While you're thinking about that, let's look at the forces acting on it. So we do still have gravity going downwards. So there's a force of the mass times the gravity going down. Air resistance, remember, goes against the motion. So air resistance this time is going up. And remember, that was 0.03 v squared. Okay, so if you've thought about what is x going to be, The best bet with pretty much any of these mechanics questions is to take the positive direction in the direction that you're traveling in, which means that this will be the point where it equals 0. The ground is going to be where the maximum height is reached because its journey is the same distance down as it was going up. So let's write our new force equation. So our resultant force, based on these two forces that are acting on our object, is the mass times gravity going in the positive direction, but the air resistance is now going in the negative direction. So it's a slightly different equation, only in terms of now this is positive and this is negative. Before they were both negative. So our mass times our acceleration is equal to mg minus 0.03 v squared. Remember, our m was 1.5. I'm just going to divide everything by that m. I'll just write over here, m equals 1.5 equals our g minus, now remember 0.03 over 1.5 was 1 on 50. So that's where that came from. So 0.03 over 1.5 equals 1 on 50, just as an aside there. So there's our equation for our acceleration when we're traveling down. Okay, so we're going to integrate this. Now we do want to know about height, and we've got velocity, so v and x. So that v dv dx formula once again is going to come in very useful. Equals, let's just subtract the fractions there, so 50g minus v squared over 50. Let's separate our variables, so v dv over 50g minus v squared equals dx on 50, integrating each side. Now, our initial v was 0 because it was at that stationary point at the top, and our velocity is going to be in terms of v. Over here, so our initial height, remember we started from back at 0, so made 0 at the top, and it's going to go down to reach a particular height. Now, last time I used x there, just to change it up a little bit, I'm going to use an h there for height. Okay, let's integrate these. So again, we're looking at a log here, but this needs to be -2. So I do need a -1/2 out the front. And then I do get then -1/2 log of that denominator, 50g minus v squared from 0 to v. So this is going to be x on 50 from 0 to h. Let's plug in those endpoints. So on this side, I've got a -1/2 out the front, a log of, again, I'm doing that subtraction trick, so 50g minus little v squared over 50g minus 0, because I'm minusing some logs, using my log laws, plug in h, and plug in 0 over there. Now, because I do have that negative log, I could actually use that negative to flip it. So let's say that's half log of 50g over 50g minus v squared. Actually, I should have times by the 50 as well. Let's put that up there, equals h. Okay, so h is equal to 25 log 50g over 50g minus v squared. So that is our equation for the height of the particle on the return journey. In part C, we're asked to find the velocity when the particle hits the ground and compare it with the initial velocity. So what we know is that the ground, the height of the ground, in this case, because remember we started at 0 at the top, so the height of the ground is actually going to be equal to the maximum height it reached earlier. And remember that was equal to -25 log 50g over 50g plus v squared. That's capital V squared. So what we actually want to know then is, when is this height going to be equal to that? So let's work that out. So 25 log of 50g over 50g minus little v squared is equal to, I realise I just said we want to know when, but it's not when, we want to know the velocity at the time that these things are equal. 50g over 50g plus capital V squared. So when does this one up here equal this one down here? Now, just because of this negative, let's put that in. Let's use our log law to flip that. And let's actually divide by 25 at the same time. So log of 50g over 50g minus v squared is equal to the log of 50g plus capital V squared over 50g. Obviously we can e to each side, so 50g over 50g minus v squared. We actually do know that these things are always going to be positive values, so 50g plus capital V squared over 50g. Now I'd like to make little v the subject here, so I'm going to start by flipping each side. So 50g minus v squared over 50g is equal to 50g over 50g plus v squared. Let's multiply by the 50g. So 50g minus little v squared is equal to 2500g squared over 50g plus, now I'm getting confused with my capitals and lowercase, that was a capital, so that is also a capital V. Now let's take the negative of each side, so v squared minus 50g is equal to negative 2500g squared over 50g plus capital V squared. Adding that 50g, v squared is equal to 50g minus 2500g squared over 50g plus capital V squared. Okay, let's just join that into one fraction. So that's going to be 50g times 50g plus v squared minus 2500g squared all over 50g plus capital V squared. These v's are all capital V's on this side, that's the lowercase one. Now if I expand that out, I've got 2500g squared minus 2500v squared, so that numerator is now just 50g capital V squared over 50g plus capital V squared. Now our velocity is going in the positive direction, so I'm going to take the positive square root. So v equals, it's the square root of all that, but I'm going to square root this v here and put it out the front. So v over the square root of 50g over 50g plus capital V squared. So in comparing this to our original one, we've got our original velocity multiplied by something. So we do need to know, is this thing something bigger than 1 or something less than 1? Is our final velocity bigger than or smaller than our original velocity? So this thing that's under the square root, this v squared is obviously a positive, so this denominator is bigger than its numerator. So therefore this thing is less than 1. And of course if we take the square root of something less than 1, then it's going to still be less than 1. So therefore the speed when it hits the ground is less than, because it's multiplied by something less than 1, less than the initial velocity at which it was fired.